Welcome to the lesson video on classification trees. In this video, we're going to talk about classification trees, which are simple classifiers. And so we're going to start by walking through an example because it's really easier to see an example and how they work. And then that'll provide a lot of understanding of what a classification tree is. And so here we're working with the heart data set, and we're trying to predict heart problems. So we start with checking for a new observation. We start by checking this thal and whether it's A, and if the answer is no, then we follow this branch, and if the answer is yes, then we follow that branch. If the answer was no, let's walk through here. We check the CA, and if that's less than 0.5, we get on here and we assign that we're going to predict heart problems. In the CA, if it's bigger than 0.5, we're going to predict heart problems. And then you check these different thresholds or variables, or check to see the value of different qualitative parameters. And then you arrive at your final nodes, or your terminal nodes, or what also called your leafs, and they tell you what to assign to that new observation. Very straightforward to use. It'll take us a little bit more effort to figure out how to train them, or talk about how do you train a classification tree. So why do we want to use classification trees? They work well with qualitative predictive variables. That's a good thing. A lot of the methods we've talked about so far, k-nearest neighbors, linear discriminant analysis, they need continuous variables, whereas classification trees work very readily with qualitative. I should say those other methods, they can work with qualitative, but it's not very natural, and there's significant problems that can come up. So why else do we use classification trees? These models are the building blocks for some of the top performing, most accurate classification methods, where you build what's called an ensemble of trees. You build lots of trees and you combine them. Also, these models are human interpretable. It's easy for somebody to see a chart like this, a series of checks, and then to apply it to an incoming patient. They're also interpretable. The person can see how it's making its decision. So if they know that there's some factor that should be changed differently, or something outstanding anomalous about the patient, they can make that decision. Another factor which can easily be overlooked, these decision trees can be checked off of a piece of paper. You don't need a computer to apply them. So if you're doing medical diagnoses for places in the world where computers aren't readily available, having it off of a piece of paper is nice. It's a good advantage. Okay, so let's talk a little terminology. Classification tree, when you make your split or your decision, you have a node where you make that decision, and then you have two branches that you can go down, one branch or the other branch. The nodes at the very end, those are called the terminal nodes or the leaves. And so just walking through some standard terminology for trees here. The one thing that's different among classification trees from regression trees, of course, we have to talk about how we assign our class. So we take all the data this was trained on, and we take all the data points that followed, say, down some sequence, and then ended up in this node, and we look at what the most common class was for the observations in our data, in our training data, that ended up in this node, and that's what we assign for that node. So what we read here is, for most observations in our training data that had thal A, and then CA had this as a no, this as a yes, this as a no, and then they would wind up down here. Most of them were no on the heart attack question. And if we want to predict probabilities, we would use not just the most common class, but what percentage of the class down here was no. We would use that as the prediction for the probability for no, and what fraction ended up with a yes was what we would use as the prediction for the probability for yes. Okay, so important question when we're building classification trees: how do we choose the variable and threshold for each split? So what we want to do with these splits is we want to divide the data into two separate sets. Separate sets go down the separate branches, and we want to divide it in a way that we've separated the classes or done something useful in separating the classes. And so over on the right-hand side, we have here an example of a good split, right? The class 2 and class 3 have been separated, which is kind of nice, but it's not the best split. The best split is down below. And so we want to walk through how software can determine, or how the algorithm for growing a tree would determine that you pick the best split and not just a good split, right? And this is just cartoon data that I've built on the right. There's 3 classes, class 1, class 2, class 3, blue, green, and orange. So here's the thing we're going to compute, a metric that'll help us determine what's called the purity of the class. So this is the purity of class K in region M. So each branch is going to build a separate region, and we want to know, are those regions separating out the data in a way that keeps class purity? And so let's think through this formula. So for a region, we look at the number of points in the region that are from class K over the total number of points in the region. So let's look at some examples. So right here we have class 1. So this table fills out, here are our classes. It fills out to can provide all the purity for all the classes in region 1, which is here, and then region 2, which is there. So let's take the computation of this. So this is class 1 in region 1. So we look at region 1 for our good split. Class 1 is the blue. So by this formula for purity, the number of points that are in class 1 is 4. That's the top of this fraction. Now we look at the bottom of this fraction, the total number of points in region 1, which is 8. So the purity is 4/8 or 1/2. Let's look at region 2. We're looking at class 1, so that's the blue in region 2, and we're going to get the same number, 4/8, which is going to give us 1/2 again. Let's look here. Class 2, region 1, we get 1/2, because in region 1, 1/2 of the points are from the green class. Let's look at how this next term is calculated as 0, or getting a different value here. So this is class 2 in region 2, and so class 2 is the green class in region 2. Right, so here's region 2, and we take the total number of points that are in region 2, which is 8, and that's the bottom of our fraction. Total number of points that come from class 2 is, of course, 0, and that's how we get the 0. So region 2 contains no members of class 2, so it gets a 0. Here we have some of the purity metrics for the best split, and we see that we're getting 1s and 0s. And so this one, we're looking at class 1 in region 1. Region 1 has 8 members of class 1 and 8 members total, so 8 over 8 is 1. Now class 1 in region 2, so here's region 2. Region 2 has 0 members from class 1 and 8 total, so that's giving us a 0. So the purity, what we really want for the purity values is something close to 1 or something close to 0. Those are our ideal scores. 1 means that region is made entirely of that class. 0 means no members of that class have gone over to that region. So here we've filled out the tables. And the way we evaluate the goodness of a split is we add up all of these purities, and that's what's called the Gini index. So when we add up the purities for all the classes, and really we do this for both regions. And so what we get here, take a look at this formula inside of the Gini index. Sorry, I think I said we add up the purities. We add up this formula for all the purities. And this formula takes the purity times 1 minus the purity. And remember we said the purity we either want it to be 0, which means no members of that class are in that region, or 1, which means that region is made only in that class. So if the purity is 0 or 1, this formula will output a 0. The more towards this half and half, not very pure regions, the larger this gets. So we compute the Gini index, which is the sum of this function applied to all the purities, and we want that to be as small as possible. So there's Gini index. We want it as small, so we're going to take the minimum. When that's small, our purities are close to 0 and 1, and our separation is good. And so here we've recreated this chart, but instead of having just a half for each of these, we have the purity. Instead of just having the purity, which was a half, we have the purity times 1 minus itself, and that gives you that product that's inside the sum for the Gini index, and then we add those up to get the Gini index for that region and the Gini index for the other region. And here's the Gini index for region 1 and the Gini index for region 2 for our best split. And you see the advantage here, this 0 in the Gini index comes because this region is made entirely of just one class, and the Gini index measures how close we are to getting to that type of state. If we used the top split, let's just think about how our tree would be built. If that was our split, then we could make another split here and then another split maybe there, and we could get perfect classification. It would take 2 more splits. This bottom, our best split, if that was our first split, we only need 1 more split, and now we're done. So we can see that this best split on the bottom is really getting us closer to our goal more quickly. The bottom line, split criteria favors splits with branches made of only one class, or branches with no members of some class, and it's this function that favors those. This is what we think about as the purity. So the split criteria favors pure regions that are pure with respect to the classes. Sometimes instead of this number, this form in the Gini index, we use a different formula which is provided here, and instead of Gini index, this is entropy. It's just a different metric. It has a similar, when you include that minus sign on the back, it has a similar shape to this. It's 0 at 0 and 1 and rises and falls in the middle, so something similar in shape to that. Just it's important to be aware. We often use a Gini index, but entropy will get you the same thing. It often doesn't make a big difference whether you choose entropy or Gini index. So once we grow our tree, we have to prune it back, because a tree, when you grow it till some stopping point, usually the minimum number of points in a node at the end, or you also stop when your node at the end is all members of the same class. And so then we generally have to prune the tree back. So full grown trees will be overtrained, and then you have to prune them back. And so here's a process of pruning. So here's what we do for each, get back to my red pen. For each value of alpha, alpha is going to be our tuning parameter. There's some subtree, so this is a subtree T within the main tree. So this means this subtree that we're going to look at is created by taking the main tree and removing some of the terminal nodes sequentially, such that this is going to be as small as possible, right? And so here's our classification error, and then this piece here is our penalty for the size of the tree. Remember, these absolute value bars here are the number of terminal nodes in the tree, so that measures the size of the tree. And alpha is how much we're penalizing for the size of the tree. We want to make that as small as possible. And so what we really get is, if this line represents alpha, if alpha is 0, we get the full tree, and as alpha changes, we'll get a different tree. So there's the full tree. As you increase alpha, you get a smaller tree. You increase alpha further, you get yet smaller, and then even smaller the further you increase alpha. So the way pruning works, you build your full tree here, and then by this construction that we've talked about here, we get a different tree, smaller and smaller as you increase alpha, and then you pick alpha according to some form of cross-validation on a training to get your error, your cross-validation error, and then that allows you to pick the tree that's going to give you the best performance, reduces your overtraining. Here's a picture on the heart data. Here's the initial full tree, And then here's cross-validation. So the tree is being pruned using cross-validation. And then here's the final prune tree. So this is the tree that gives you the least error through cross-validation. So just to review what we've talked about today, we've talked about building classification trees. And classification trees you build sequentially, meaning you build one node and then the next going down. And you do that maximizing purity at each node. And then once you've built your full tree, you scale it back using pruning, and that avoids overtreating. Why do we use trees? They work well with qualitative predictor variables. These are building blocks for some of the most accurate methods, and they're easily human interpretable, easy to understand by people directly. Some people say they mimic the way people make decisions and think. Thank you very much for watching.